Welcome, and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields, and strengthen ties between Michigan State University and the community. Today, we have the pleasure of presenting a public lecture by Professor Brian Metzger entitled Gravitational Waves How Gravitational Waves Pointed Us to the Origin of Gold. Professor Metzger received his bachelor's degrees at the University of Iowa and his PhD in physics at the University of California, Berkeley in 2009. He held a NASA Einstein postdoctoral fellowship at Princeton University before joining the Columbia University Department of Physics in 2013, where he is currently a full professor. He is also senior research scientist in the Center for Computational Astrophysics of the Flatiron Institute. Professor Metzger's contributions and recognitions include the Sloan Fellowship, the New Horizons Breakthrough Prize in Physics, the Bruno Rossi Prize of the American Astronomical Society, and the 2020 laureate of the Zlatnik Awards for Young Scientists. He is supported as a Simons Investigator by the Simons Foundation. If you have any questions during this talk, please type them into the chat or the question and answer dialog box. Now, at this time, it is my great pleasure to introduce Professor Metzger.
Thank you, Dean, for the introduction, and thanks everybody for joining on what's a pretty dreary day here in New York City, but I'm pleased to talk to you about science today. I apologize, my voice is a little bit hoarse because I'm getting over a cold, but hopefully that won't be too big of an issue. Today I'm going to tell you what is really, I think, an amazing story that unfolded now about 6 years ago, when for the first time we detected gravitational waves from the merger of two neutron stars. And how by studying that event and the light that was produced by that event, we were able to conclude that it's likely that this event was creating some of the heaviest elements in nature, which the origin of which, has been a long mystery, still remains a mystery in detail. But this one event really advanced our understanding considerably. And it was just extremely exciting from the standpoint of the way it engaged such a large fraction of the astrophysics, nuclear physics, gravitational wave communities, and really brought these fields together to study this outstanding event. And really, this is just the beginning, we hope, of a new era of so-called gravitational wave multi-messenger astrophysics, where we're really combining the information from light, electromagnetic waves, gravitational waves, and our knowledge of the fundamental properties of nuclei and of matter to hopefully obtain a better understanding of the universe. So this is my goal today, is to excite you about this topic, tell you the story of this event, and convince you of the path ahead. Okay, let's see. So one of the areas I work in is nuclear astrophysics. And, one of the goals of nuclear astrophysics is to identify when and where in our universe the elements that make up the periodic table were forged. And as you go to the top of the periodic table, we have, quite a bit of knowledge about where these elements are created. And as you move down towards the bottom, it gets less certain. So for example, when I started graduate school, well, actually, when I was in graduate school in 2008, this is kind of, if you open a textbook, this is what it said. The elements were created. We knew that hydrogen and helium were formed in the Big Bang. The intermediate mass elements, the elements of life, many of these are created in stars, often massive stars, and expelled into space when those stars die as supernova explosions. How do we know this? Well, we can go out and directly observe the explosion of stars. This is a remnant of the Cassiopeia A remnant. This was a supernova that happened in our galaxy, maybe the last naked eye event you could have actually observed with your naked eye if you'd been outside in the year 1667. And of course, by this time, 350 some years, the material that was ejected when this very massive star exploded, which it was estimated was about 17 times the mass of our sun. As that material expands into space, it collides with the gas surrounding the star and the winds that were expelled by the star before it died. And this shocks the material and causes it to glow in X-rays. And, by observing, in this case, different X-ray frequencies, different X-ray energies, we can actually infer what types of elements were created in this explosion, and we're seeing them directly being expelled out into space, ultimately to see the next generation of stars, the next generation of planets. So as I said, in this case, the quote unquote red X-rays were coming from silicon, the yellow ones from sulfur, the green ones from calcium, the purple ones from iron. And so this is really the motivation for this famous quote from Carl Sagan, that the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interior of collapsing stars. We are made of star stuff. And the reason Carl Sagan was so confident in that are observations like this, where we can actually directly go out and observe these exploding stars and see them seeding the universe with these heavy elements, and how they're created in the stars, how they're produced when the stars explode. In some cases, how those elements are expelled into space are really, topics that remain of current interest. But, by and large, we're pretty confident where these elements come from. But as you get to the bottom of the periodic table, the elements heavier than iron, these are much less abundant in the universe and on Earth. And roughly half of these elements, until very recently, we had, I would say, very little idea at all where they come from. These are the so-called rapid neutron capture process elements. I'll come to what that means in a second. But this includes precious metals like gold, silver, and platinum, transuranic elements like uranium and plutonium. You can certainly imagine that the way that our society on Earth evolved, the conquest for gold in the New World, the things we have to deal with nuclear warfare, etc., would have evolved very differently if these elements existed in different abundances, if they were rarer and more common on the Earth than they are. And so it's, I think, of fundamental interest, if not just for the way that society evolved, to know where these elements are coming from in our universe. And the fundamental challenge and why they're so rare is that we can create elements up to about iron inside of stars. So iron is a nucleus, with of order, 26 or protons, and roughly the same number of neutrons. But a much heavier element like gold, has many more neutrons than protons. And as the star evolves, you can create heavier and heavier elements as the core of the star gets hotter and hotter. But it's difficult to go much beyond iron. Because as eventually you get so hot in the interior of the star that the nuclei just want to sort of photodisintegrate rather than actually create heavier elements. You have to overcome the Coulomb barrier to form elements through nuclear fusion, and this gets harder and harder as you go to more massive stars. But in principle, of course, this has been an old problem of how you turn a relatively common element like iron into a rare, precious element like gold. In principle, it's straightforward. You just take an iron nucleus and you bombard it at a really high rate. I usually have a movie of this, but you take an iron nucleus and you bombard it at a really high rate with neutrons. And these neutrons, of course, can just overcome the Coulomb barrier. And you can create a heavy radioactive isotope that ultimately decays into gold. So the question of where these heavy elements come from, they're formed by taking a lighter nucleus and bombarding it with neutrons. The question then shifts a little bit. Where in nature can I find such a high abundance of neutrons that I can bombard iron nuclei, for example, and turn them into gold? And this is a challenge because, of course, neutrons are unstable. They decay back into protons in vacuum in about 15 minutes. So where do I have, such a high abundance of neutrons in nature? Well, an obvious place to look are neutron stars. These are the very dense relics that are created from the leftover core. When a massive star collapses in on itself at the end of its life, in its center, it forms a very compact ball of neutrons called a neutron star. And it's essentially the gravitational energy released by this collapse that is ultimately responsible for blowing up the rest of the star, the outer layers of the star, which expand into space, as we saw with the Cassiopeia A remnant here. But in the center of the Cassiopeia A remnant, what you see, we're seeing X-rays here, you see is a point source of X-rays. So this point in the middle, this dot, is a hot, cooling neutron star. So you can actually directly see in this image what was created by this explosion. A neutron star is essentially what you get if you take something of order the mass of our sun, but compact it into a star the size of roughly Queens. Right now, I'm sitting in my office here in Upper Manhattan. This is a bit dangerous of a image to take through security at the airport for various reasons, but you know, the properties of neutron stars, of course, are still quite a bit uncertain. They're not completely made of neutrons. You still need some protons around to provide the electrons, which actually keep the neutrons stable. So neutrons are able to remain stable in a neutron star because, unlike in free space, because the Fermi sea is full, essentially it's forbidden for them to decay into protons. But still, neutron stars are mostly made of neutrons. And they're extremely dense. You know, the usual statement you'll hear is that a teaspoon of neutron star material weighs as much as a mountain. So these exotic objects do exist. As I said, we actually see them in the centers of supernova. We see them in other contexts as rotating radio sources known as pulsars, which is actually how they were discovered by Jocelyn Bell in the 1960s. The other ingredient I need to explain to you is, in very rough terms, is Einstein's theory of gravity. So in essence, you know, Einstein, of course, in the early 20th century, modified our view of gravity from the original Newtonian view. And to summarize his elegant equations in one famous sentence from John Wheeler, the notion is that, you know, mass tells space-time how to curve, and space-time tells mass how to move. So space-time is, of course, you know, the fabric that we live within. And the notion is roughly as follows: rather than thinking about a satellite orbiting the Earth, you think about a satellite going in a straight line, but the Earth has redefined what is a straight line. A straight line is no longer straight. The space-time is curved, and so the satellite orbits the Earth, or appears to orbit the Earth, because of the distortion of space-time created by the mass, the very heavy mass of the Earth. And so if you think about different types of stars, an object like the sun, while quite massive, is rather large in size, and so its distortion of space-time is relatively moderate. On the other hand, when you have a neutron star where you're packing in the mass of the sun into a size of only 10 kilometers or so, you know, that distorts space-time even more. It's almost as much as you can distort space-time and not have the third object I've displayed here, which is a black hole. And a black hole is, of course, when you pack in a solar mass into something smaller than a few kilometers. And in this case, the gravity of a black hole is so strong that not even, you know, light can escape from it. So light can get out of a neutron star. We saw it glowing as X-ray source. But a black hole is so, the mass is so concentrated that not even light can escape. And we now have pretty good evidence that, you know, both neutron stars and black holes exist in our universe. I'll come back to that in a second. But getting that out of the way, the other thing I want to emphasize to you is that while our sun is a single star all by itself, many stars in nature are actually orbiting other stars in binary or even triple systems. So this is, since this week is the week of May the 4th, I thought I would show you the most famous binary star system, which is the one that around which Luke Skywalker's home planet orbited. And so he was able to see a twin binary sunset of two stars sunsetting, because his planet was going around both the stars, which were themselves orbiting each other. And so the notion here is that when you have two stars that have roughly the same mass, rather than thinking about one orbiting the other, you really think about both of them orbiting around a common center of mass. And binary stars are very common in our universe, as I said. Essentially, every type of star exists in a binary, either with a star of its own type or a star of a different type. And this is also, we believed, true of objects, exotic objects like black holes and neutron stars, which, as I mentioned earlier, are formed when more massive stars die. So if you get two of these very compact objects, black holes or neutron stars, orbiting one another in a binary, over time, that orbit doesn't remain stable at a single radius. Over time, that orbiting bodies move closer and closer together. And the reason they do this is because, according to Einstein's theory of relativity, if you have two objects orbiting one another, they're emitting something known as gravitational waves. These are like sort of ripples in space-time, distortions of space-time is the way to think about them. And these gravitational waves, which I'll come to in a second, carry away angular momentum and energy from the orbit. And so over long periods of time, they can actually drive the two stars to come closer and closer together and ultimately coalesce into a single object. This is a sort of runaway process. It's very slow when the two stars are very far apart. I'll show the movie again. But it accelerates as they move closer and closer together, as they move faster and faster. This rate at which they emit energy to gravitational waves accelerates in time. Technically, the Earth going around the sun also emits gravitational waves. It does, but it's extremely slow, and it won't move appreciably due to this in the entire age of our universe. But for these compact objects like black holes, and I'll come to in a second, neutron stars, they can actually emit gravitational waves and coalesce over the timescales that we can actually directly observe. So when one of these gravitational waves, for example, from two merging black holes, is happening in some distant galaxy, but those ripples in space-time are propagating in all directions, including occasionally passing through the Earth. And so these gravitational waves, as they pass through the Earth, cause these local ripples in space-time. This is a bit of an exaggerated view of this. Of course, the Earth is not being stretched and compressed that much by the gravitational waves. It's a much more subtle effect than this. But this offers us an opportunity to actually detect these gravitational waves, to actually see, if you will, the mergers of these compact objects in distant galaxies. And as I mentioned to earlier, these waves get stronger as the two stars get together. So it's kind of crescendo in terms of the gravitational wave signal. So it wasn't until the last, 10 or 20 years when we've had the capability to really seriously search for gravitational waves directly on Earth. And the most successful endeavor in this regard, which made the first detection of gravitational waves, was the Laser Interferometer Gravitational Wave Observatory, LIGO. There are two LIGO observatories right now, one in Livingston, Louisiana, and one in Hanford, Washington State. They need to be separated by a large distance across the United States, because when you measure these gravitational waves, being separated further apart gives you more sensitivity and the ability to rule out other sources that are not gravitational waves. So the way these detectors work, in very brief, they could give an entire talk on the amazing technology that went into developing LIGO over the last, even 50 years. But roughly the way it works is that you have two perpendicular arms to the detector, several kilometers in length, and you send a laser beam down both arms. And if there's no gravitational wave passing through the detector, then the two lasers, as they return back to the source, they destructively interfere, and so no light is appearing on the plate over here. But when a gravitational wave passes through, it induces very tiny distortions in the time or the length, if you will, that the light has to travel around each of the arms. And that tiny differential change in distance induces an interference pattern that can be observed. And it's to give you a sense of how sensitive this detector has to be to detect gravitational waves. It's measuring in effect a difference in path length between these two arms of a size less than an atom over their several kilometer lengths. It's really an incredible technology that they could be sensitive to these extremely tiny distortions of space-time due to these admittedly very violent events that happened very far away. So in September, I guess it was 20th of see if I can minimize this, of 2015. Oops, moving. Okay. Lost my ability to change the thing. One second. Okay. Yeah, so in 2015, these gravitational waves were detected from the first time from LIGO. This is showing you the strain of the gravitational waves, basically how powerful they are in the two detectors in Washington State and Livingston, Louisiana, as a function of time. And as I mentioned, as the two black holes in this case move closer and closer together, the signal they produce gets stronger and stronger. And since they're moving faster and faster, it also increases in frequency. So if you could actually hear this, it sounds like a chirp, like maybe I can actually play it like that. And what they were detecting were what I showed you earlier, which was two merging gravitational waves from two merging black holes, excuse me. Now I can't turn it off. But essentially, this discovery of gravitational waves from, I'm going to go off this page and come back. This discovery of gravitational waves from the merging black holes led to the Nobel Prize for these three individuals in 2017. You know, in this case, the two black holes each were around 30 times the mass of our sun. And since, let me see if I can hide the, there it goes. Since that discovery back in 2015, LIGO has detected now actually 50 of these merging black hole systems over the last several years. I'm just showing you an ensemble of the first few here, where here is the masses of the two black holes. This case, you know, a 35 solar mass and a 30 solar mass merging to form a 60 solar mass black hole, for example. But there, as I said, there are now 50 of these sources. But essentially, none of these emitted any light, as far as we could tell when we looked with our telescopes at these sources. And this is not surprising because, you know, black holes are in some sense pure space-time. So if you merge the two black holes together, gravitational waves are emitted, but no light is emitted. So it's not so surprising that we other than LIGO, we couldn't see these events happening in any other electromagnetic wave band. But this is different if we replace the two black holes with two solid body objects like neutron stars. As in the case of black holes, two neutron stars will also do this dance if they're in a binary system and coalesce over time. But unlike black holes, because they have a solid surface, because they're made of actual matter, when the two stars slam together, they can actually eject material into space, which can emit light or, you know, other sources of electromagnetic radiation that we could directly observe with our telescopes. And so this was really sort of for the people who were, you know, who are astronomers who had telescopes who wanted to actually see something. What they were really waiting for was from LIGO was the detection of two merging neutron stars. And they were fortunate to get such an event on August 17th of 2017, around 8:40 in the morning Eastern time. The LIGO detectors detected for the first time these merging neutron stars. So here you're seeing the frequency of the gravitational waves versus time. And where you see lighter colors is showing you where the signal is. And so you see this track begin to appear in Livingston, certainly, and Hanford, that's sort of rising in frequency and amplitude. And this is the chirp signal from the two merging neutron stars that was seen on this morning on August 17th. And you could tell it was a neutron star because the black holes tend to merge quite quickly, whereas the neutron stars, because they're lighter, they take a lot longer to inspiral. In this case, you can see at least tens of seconds. And so after they made this discovery, you know, the astronomers of the world were very excited. They wanted to try to find the electromagnetic emission from this event. And so one of the first things you'd like to know is where it was occurring on the sky. And the way this is done is as follows. Essentially, the gravitational wave source, they can measure precisely when the gravitational waves arrive at the detectors, the gravitational wave detectors. I didn't mention this, but in addition to the 2 LIGO observatories, there was a third gravitational wave observatory in Italy that was involved with this discovery called Virgo. And so by measuring when the gravitational waves arrive in Louisiana versus Hanford, Washington versus in Italy, they're able to pinpoint on the sky where the source is coming from. And in this case, they inferred that the neutron stars were coming from the constellation of Hydra.
So Brian, perhaps this is a good place to ask a question in the question and answer. How fast do gravitational waves travel?
As far as we can tell, they travel exactly at the speed of light. In fact, we saw a burst of gamma rays come from this event I'll talk about in 1 second. And right when the 2 stars coalesced, and they arrived coincident with the gravitational waves to within 2 seconds after traveling over 100 million light years. And we think that 2 seconds is probably shorter than that. So we have very good constraints that they travel almost precisely at the speed of light. And that's what Einstein's theory predicts as well. Is there any other questions? I can't see the...
No, that's it for now.
Okay, please. Yeah, I'm happy to stop and answer them at any point in time. Okay, so what happened? Okay, so these 2 neutron stars merged in August 17th, 6 years ago. LIGO sort of told us where to look on the sky. This is kind of what went down in the next 11 hours or so. So basically, the first thing that happened is actually within 2 seconds of when the 2 stars merged, there was a burst of gamma rays that was detected by NASA's Fermi satellite coming from this part of the sky. The Europeans have a gamma ray satellite called Integral, which also detected the source and knew it was coming from this band. So at this point, they knew it was coming from this part of the sky. A few hours later, the LIGO interferometers, based on this triangulation technique I mentioned, localized it to this region, and then the Virgo detectors. And so at this point, they knew it was coming from one of these galaxies within this 30 square degrees of the sky. And a bunch of optical astronomers using the Swift's telescope in space, as well as ground-based telescopes, basically sifted through all of the galaxies within this region of the sky, and they discovered the fading counterpart in this galaxy called NGC 4993, which, as I mentioned, is about 130 million light years from the Earth. This sounds like a very large distance, but it was actually quite a bit closer than we expected the first gravitational wave source to occur. We didn't think the galaxy would already have a name. Many, as you go farther away, the galaxies don't have sort of names assigned in the 19th century, but in this case, it was relatively nearby galaxy. So what did they actually see? What was it that these telescopes that, and this sort of chase to find the counterpart involved, it was estimated like a third of the astronomers in the world. There were several competing groups that were all trying to find it. A number of, independent claim discoveries. Really the first to, I think, discover it was this SWOPE telescope in Chile. I was involved with the dark energy camera, which also made an independent discovery of it. But what did they actually see? What they saw was a flaring, rapidly fading flare of light that was really unlike that had ever been observed before. So this is the galaxy itself, and you can see that little point in light. The first observation wasn't able to commence from the ground until about 11 hours after the discovery, because it happened over the Indian Ocean, and most of the big telescopes are in South America. So you had to wait for the Earth to rotate for it to be nighttime in Chile. But it was discovered about a half a day afterwards, and then the astronomers monitored its fading over the following weeks. And we see supernova explosions all the time, but this was fading much faster and had very different colors than the supernova we see from ordinary massive stars exploding. And so the rest of the story I want to tell you today is how basically we immediately knew what we were seeing because theorists had been working for a long time on predicting what we would see from these events, and those predictions came true. We actually saw from this event evidence that these heavy elements I mentioned earlier were created during this merger. So to show you what happened, I need to show you a simulation of two merging neutron stars. This is less of a cartoon simulation. This is actually a hydrodynamic simulation obtained by solving Einstein's theory of general relativity, including the physical properties, we think, of the neutron stars, including all of the relevant hydrodynamics as the two neutron stars coalesce. So this is, should say, courtesy of David Radice at Penn State. So what you're seeing are the final few orbits of the neutron stars as they move closer and closer together. This is all occurring within a matter of milliseconds. And the two stars, as they get closer together, they start to, one of the stars starts to tidally distort the other one. And then eventually the two objects get torn apart and they form a massive, a rapidly spinning object that ultimately collapses into a black hole. Let me show you that again. So we're seeing the final few orbits. The two objects begin to tidally squeeze each other. There's some matter ejected out from the outer Lagrange point of the binary. The two stars ultimately coalesce, basically shooting a bunch of debris in all directions. And then some of the matter ends up orbiting around what becomes the newly formed black hole in the center, surrounded by a disk of material. So if you merge two neutron stars together, it turns out that the object you form is generally too massive to remain a neutron star. It becomes unstable and collapses into a black hole. But because the initial binary had so much angular momentum, some of the neutron star guts, if you will, remain outside of the black hole, orbiting around it in a torus of material. It's actually this torus of material that we think powers an outflow of material that a relativistic outflow that produced the gamma rays that we observe from that event. But that's a little bit of a different story. So this torus of material, so it turns out that black holes in this context are fussy eaters. So after you form the black hole as the two neutron stars merge, there's this disk of material which is orbiting around it. And so this is some a simulation that we did, again, by solving Einstein's equations of, in this case, of magnetohydrodynamics. So hydrodynamics, including the role that magnetic forces, electromagnetic forces play. So you're seeing basically a slice through, this is the top view, and this is a side view of this accretion disk that formed around the black hole. And as you start to feed material onto the black hole after the merger, only a fraction of that material actually falls into the horizon of the black hole. The rest is ejected into space in all directions in the form of outflows from this accretion disk. And again, the best way I describe this is that you can't, you try to feed a black hole at a very high rate and it doesn't really want to accept all of the material. Some of the material will be unbound into space surrounding the site of the merger. And importantly, because in part, this torus of material was formed from a neutron star, the material in this torus is extremely rich in neutrons. There are many more neutrons than protons in this material. So as these disks are unfathomably hot and dense, the temperatures are several billion Kelvin, tens of billions of Kelvin. The densities in these accretion disks are 12 orders of magnitude higher than the density of water, for example. But as this material expands away from the accretion disk, this is now zoomed out on a much larger scale. And each of these little spaghetti lines here is a fluid element of material that is flowing out away from the black hole into space. As this neutron-rich material flows outwards into space, it is able to create these heavy elements, as I discussed earlier. Essentially, what happens is it's a little bit like the Big Bang. The neutrons and protons get together and form helium, but in this case, it's dense enough that the helium nuclei are then able to undergo triple alpha, forming even heavier elements. So you create very quickly in the expanding material these sort of iron-like elements, but there are so many neutrons left over that these iron nuclei are then bombarded by the neutrons at very high rates. And it's this way that you can create these heavy elements like gold in the ejected material. So here's an iron nucleus that was just formed out of what was initially free nuclei in the accretion disk. It flows out, it forms iron, and then the iron is bombarded by neutrons. And in this way, it's able to create a heavy radioactive isotope, which once it stops eating neutrons will decay back into a stable isotope. So Census, as an audience that I am understanding, has some familiarity. This is sort of the most technical slide I'll provide, showing the way, a little bit more detail, the way that you form these heavy elements. So this is the proton number on this axis, and this is the neutron number on this axis. You're probably familiar that the stable isotopes are sort of in the valley here. And what we're following, and the colors we're following here, are the abundances of the material in a single one of these fluid elements, which is expanding from very high temperatures and very high densities. And as this fluid element expands, we're just going to follow the nuclear reactions, the neutron captures, which move nuclei this way, the beta decays, which move nuclei this way. There are also alpha decays and fissioning going on. And we're just going to see how we're able to start off with these are elements not much heavier than iron, the so-called seed nuclei. We're going to see how we're able to capture, and then you could see the time is listed somewhere up here. The time since the material is expanding. So this is just a few milliseconds after the material is ejected. And so what we're going to see is that we're now capturing neutrons, beta decaying, capturing, and within a matter of seconds, we formed isotopes all the way up to these very heavy ones. And about a second later, we're out of neutrons. And now over the ensuing days, weeks, and months, and years, this matter expands, decays back to the stable elements. Let me just show you that one more time here. So we start off with the seed nuclei at basically 10 milliseconds after the merger. And as our density and temperature drop, as this material expands, we are able to capture up to these heavy elements. And then eventually, when we run out of the neutrons, we decay back. And I want to emphasize that these are it's the properties of these nuclei well off of the stable valley that are one of the most uncertain aspects of these simulations, and are exactly the kind of things that FRIB is measuring. And this is another way of thinking about it is that these nuclei, which exist only for a few seconds after a neutron star merger, are the kind that you're producing there in Michigan, and really are a crucial input for us to translate our theoretical models for what happens after the merger, the hydrodynamics, into the exact abundance pattern of these nuclei that are created, to know whether these sites are really important sources for creating the heavy elements. But the important point for what we saw was that we create all these radioactive isotopes, and as they decay back to stable isotopes, they're releasing heat, just in the same way that radioactive waste produces heat. And this keeps the expanding material from the merger hot. If it didn't have this heating, it would just cool adiabatically, and we would never be able to see it from such large distances. But this radioactive material keeps the ejecta hot and causes it to glow. And this allows us to produce a detectable signal that we could actually observe from 130 million light years away. And so in 2010, I worked on some of the first predictions, quantitative predictions for how these events, how these neutron star mergers would appear to an optical telescope. And we predicted at the time that these events would be about 1,000 times brighter than what we call a nova in our own galaxy, and that they would last about a day before decaying away. And we called them a kilonova because it was 1,000 times a nova. A typical nova in our galaxy peaks at around 10 to the 38 ergs per second in luminosity, and these were about 10 to the 41. But in retrospect, we probably should have just called it a radioactive waste nova, because that's essentially the physics, that we create all this radioactive waste and we expel it into space. So the amazing thing on that August 17th day, when I first heard that they had detected a counterpart to the merger, was it would be an opportunity to test our models for whether we really did see a kilonova appearing after the coalescence of two neutron stars. This event I showed you earlier, which peaked very early and then faded away over the ensuing days. And so it was quite striking when we were able to actually compare our models to the observations, that they matched strikingly well. And so it was apparent that this is what we were seeing. There was really no question. We see an unusual explosion happening in a galaxy, which just happened in the direction that LIGO detected a merger, which has the properties that were theoretically predicted from a neutron star merger. So this was very exciting because in detail, this light curve is telling us something about how much of these heavy elements were created, what the composition of those elements were, things like how fast the material was expanding. One of the interesting aspects of the emission that we saw from this kilonova, from this neutron star merger that LIGO detected, was that the early parts of the emission in the first day were extremely blue in the colors. And then over the ensuing weeks, the emission got extremely red. And I don't have time to go into details, but this color evolution told us something about the composition of the material. The bluer material, we think, is mainly comprised of lighter heavy elements. So things, around the first R process peak, around, xenon. And the redder material is coming from, we think, some of the heavier elements, the lanthanide and actidide elements, which are on the very bottom of the periodic table. And so by mapping out the geometric distribution and contributions of these different types of elements, we can start to create a model for, I'll show you this model for, again, of how what contributed to the expelled material from this event. So as I said, we sort of inferred that there was a sort of a bipolar component of lighter R process elements, and then a more spherical component of the heavier ones. So this was quite exciting. This is the first time that we had directly observed in nature the origin of these R process, rapid neutron capture process elements. It was a process that was identified as being the origin of these elements back in the 1950s, essentially almost 70 years ago. And this was the first time we had seen these in nature. This one event was really a veritable gold mine in terms of what we inferred it produced. It ejected in total about 5 times the sun's mass and material, of which, if it did have the composition, the relative abundance ratios of the solar system, our process, would correspond to around 10 times our own Earth's mass in gold, 50 times in platinum, and maybe 5 times the Earth's mass in uranium. Now this, it seems like an enormous amount of material, a very high yield of material, but these neutron star mergers are extremely rare. They only happen in galaxies like the Milky Way every 100,000 years or so. But nevertheless, if you take this quantity and multiply by that rate, and you figure out how many of these mergers happened prior to the formation of the sun, it is certainly plausible that these types of events could have been responsible for most or all of the precious metals and ultra heavies on Earth, which is quite striking because, it tells me, for example, if this is true, that, the platinum on my wedding band may have been at one point, that material may have been one point, a few kilometers from falling into a black hole, expelled into space, and then formed these elements. It gives you quite a perspective on the special experience that these elements achieved relative to most material in the universe. But anyways, so needless to say, we still don't really know the details of the origin of the bottom of the periodic table. My textbook in 2008 told me that these elements were all produced in supernova. we've sort of modified now the latest version of this has sort of shifted, where now it says that these elements were all produced from merging neutron stars. So in some sense, we've changed the textbook in 10 years. But what I would say is we don't really know that yet. We've seen one event. We don't really know if these are the only sources of these elements. There's a lot of interesting things happening out there in the universe. As LIGO detects more of these mergers, as we're able to identify and characterize their kilonova emissions, and use our nuclear physics knowledge to really ascertain what that's telling us, I think we will have a more complete picture. So stay tuned and be skeptical of the periodic table you might see in your textbook, at least an astronomy textbook. Here's the final sort of artist impression from NASA of this merging neutron star. I just like to show it because it's pretty. So the two coalescing neutron stars, which eject this radioactive material into space as they feed a newly formed black hole, which creates a jet of material, which goes out and makes a burst of gamma rays, as well as ejects this cloud of basically fireworks into space, which gave us the kilonova that we see. I didn't even get a chance to talk about the X-ray and radio emission produced by this jet, but that's another aspect. So the future in this field is extremely bright. Starting actually right now or next month, the LIGO and Virgo interferometers are starting their fourth observing run. They will be joined for the first time by a Japanese detector gravitational wave observatory underground called Kagra. The LIGO observatories are adding a additional third observatory to India. And the importance of having these spread across the globe is what I said earlier, that they determine the location of the source on the sky by the arrival time. And so if you spread these detectors out, you can better determine the location on the sky, which is really important for astronomers that are trying to search and find these relatively dim, fast evolving signals. So what we're hoping is to see additional neutron star mergers from different angles. We're hoping to see them for different properties of the ingoing neutron star, for different masses of the two neutron stars. This is, we hope to use to constrain our knowledge of what neutron stars are actually made of. We also hope to detect the mergers of neutron stars with black holes. Actually, in the last observing run a few years ago, LIGO did detect through gravitational waves the mergers of a few neutron star black hole binaries. But the black holes were so big in those systems that they essentially ate the neutron star whole. And so we didn't actually expect to see any light from those systems either. But for less massive, smaller black holes, we think that they could tear apart the neutron star, also ejecting some of that material into space and creating radioactive elements, creating a kilonova. So we're hopeful to detect kilonova from neutron star and black hole mergers. And ready in the waiting for all this are astronomers around the world who have positioned telescopes to be able to follow up these sources both on the ground and in space. So I'm really hopeful that the next decade will be a golden era in this field. So I just want to personally give a thanks before I finish, send a thanks out to my research group at Columbia, on which I worked on many of these topics, and to point out that I've received invaluable support from a number of federal agencies, as well as private agencies. So with that, I will stop and take your additional questions. Thank you.
Great. Thanks so much, Brian. That was a beautiful talk. It's a really great science story that had a really exciting ending, but it continues on. So there is a question from Chris Gould. How well understood is the equation of state for the neutron stars involved in the merger calculations?
I guess the answer, great question. I guess the answer is a little bit related to defining how well. It certainly is true that that what is currently done is to assume, given a certain equation of state, which produces radii of the neutron stars and masses of the neutron stars, which are consistent with observations of neutron stars in our own galaxy. But this can really matter if a different equation of state predicted a different radius, or it really, one of the most important things that is the Tolman-Oppenheimer-Volkov mass, the maximum mass that the equation of state maximum stable mass of a neutron star defined by the equation of state. If that is larger, if the equation of state can support a more massive neutron star, then after the merger, the remnant tends to survive longer. And I didn't mention it, but how long the remnant survives before a black hole forms could have a really important role in what material is ejected, how strongly irradiated that material is by neutrinos from the remnant, which is very hot until it makes a black hole. So it's not particularly well understood, but we have some constraints. But our hope is to reverse engineer this, and by detecting enough mergers, which LIGO measures, which span a range of different masses for the ingoing binary, we're hoping we can work backwards and learn more about the equation of state. LIGO also, just from the gravitational waves alone, can actually constrain the radius of the star. And based on their observations of this event, they put an upper limit of around, I think it's around 13.5 kilometers on the neutron star size. But we're also getting constraints from the nuclear physics side on, neutron skin thickness affects aspects of the equation of state, which control the neutron star radius. So yeah, it does depend on that. There's a lot of both experimental and observational work that is honing in on that.
Thanks, Brian. There's a question from Bill Robinson. What about detecting a neutrino burst from neutron star mergers?
So that's certainly something we hope to do. There definitely are neutrinos created by the post-merger object before it makes a black hole, and from this accretion disk, which is feeding the black hole. The problem is, and these are mainly thermal neutrinos with energies of around, tens of MeV or so at most. The problem is that the amount of neutrinos emitted is not significantly more than you get from a core collapse supernova. But core collapse supernova are about 1,000 times more common in our universe than these. So once we have neutrino detectors like, Dune, that are detecting, many core collapse supernova, we may eventually be able to detect one of these, get lucky enough to have one close enough. Those are the MeV neutrinos, which we are quite confident are there at some level, but are hard to detect. There may also be a possibility to detect high energy neutrinos with, for example, the Ice Cube Observatory on the South Pole. But the production of those is more sensitive to what's happening in the jet from the black hole, whether it accelerates non-thermal particles and whether those particles make neutrinos. So that's far less certain. But if we get an event where the jet is pointed towards us and those neutrinos are beamed towards us, there's certainly a chance. And I think that is perhaps the more likely route is sort of TeV or PeV neutrinos with Ice Cube, but we'll see. Haven't seen it yet.
Actually, related to that, I had a question again about future observations in optical or X-rays. So it's difficult, I know, with the kilonova, there's so much going on. There's a lot of Doppler shifting to see individual lines. But in the future, do you think we could get more information about abundances of specific elements?
Yeah, so I didn't mention this, but in the optical kilonova we saw, there actually were absorption features in the near infrared that were attributed to specific elements. So there was a claim of a strontium line, but there was another group recently which said it might also be a helium line. You do get a little bit of helium from the alpha-rich freeze-out of forming these heavy elements. And so I think the problem is that there's just so many lines. There is a certain degeneracy, and as you said, they're Doppler broadened by 0.1 or 0.2 C. I don't know if I even said that, but this matter is expanding at a significant fraction of the speed of light. So I think we need more theory work, but I think there is promise. More hopeful I am is regarding late time in the nebular phase. Several months after the merger, where you're seeing all the way to the center of the ejecta, the slowest material, which may have narrower lines, probably emitting in the infrared. I think pointing the James Webb Space Telescope at one of these mergers in the infrared, we may be able to identify some narrower lines in the infrared from specific R process elements. So I'm looking forward to that. Yeah.
That'd be very exciting. All right, I don't see any other questions, so let's close then the formal part. And if somebody wants to ask a question private, we will open that up. But otherwise, thank you, Brian, very much. Thank you, everybody, for coming. Have a great rest of your weekend.
Thank you.